Periodic functions are functions that model phenomena that repeat with a predictable pattern. So examples include the tides, the phases of the moon, hours of daylight in a day. All of these things can be modeled by sine and cosine functions. These functions are periodic, which means that their values repeat in regular intervals or periods. And so we're going to see one period of each of these functions and then know that that period should repeat across the graph over and over and over again. So if you don't have your unit circle out, please grab it because we're going to need some of the values of sine as we start to build or look at the graph of the sine function. So let's first fill out the table and then we'll take the table and do all the coordinate points. What is the sine of 0? 0. Nice. What is the sine of pi over 6? 1/2. What is the sine of pi over 2? Oh, I jumped. Pi over 2. It's 1. How about 5 pi over 6? 1/2. What about pi? 0. What about 7 pi over 6? -1/2. How about 3 pi over 2? -1. How about 11 pi over 6? -1/2. And then back at 2 pi? 0. So we have all of these input value pairs. Obviously, I jumped around the unit circle a lot because I wanted points that were easily plottable. Because like square root 2 over 2 and square root 3 over 2, we don't naturally know where that number is. But if we start to plot all of these points, we have 0, 0, pi over 6, comma 1/2, pi over 2, comma 1, 5 pi over 6, comma 1/2, pi, comma 0, 7 pi over 6 and -1/2, 3 pi over 2 and -1, 11 pi over 6, -1/2, and 2 pi back at 0. When we play connect the dots, we do get this wave that goes up and then comes back down before it goes back up again. This is the sine curve. We're looking at the features of the sine curve, and these are the features that we're going to be writing down for each of the functions as we go. So however you orientated this on your paper, you can write them on there. I'm just going to go underneath it a little bit. First thing we're going to talk about is the domain. The domain of this function would continue on from -infinity to infinity. So its domain is all real numbers. Obviously, we only graphed between 0 and 2 pi. But we do realize that this graph would keep going this direction and this direction on and on and on. For the range is telling me to describe where the graph shows up for the y values. So what is the lowest value that this goes to? -1. What's the largest value this goes to? +1. So the range of this graph is between -1 and 1 inclusives, because I can actually touch -1 and 1, so we use the brackets. Which means my maximum value is 1 and my minimum value is -1. We're also going to write down where the zeros of this function show up. By zeros, I mean x-intercepts. Where do you see, there's 3 of them on our graph, where do you see the x-intercepts here? 0 and do you see a pattern here? The zeros are going to show up on this graph every time that we have x equal to 0 plus 2 pi k, where k is an integer. So that means and every rotation after that. So that's 0, that's 2 pi, 4 pi, 6 pi, 8 pi. See what I'm doing there? But you guys also saw that the 0 occurred at pi, so we have a second place, which would be pi and every rotation of the unit circle after that. Pi and 3 pi, 5 pi, 7 pi, 9 pi. Great question. K stands for an integer, so K is an element of the integers, meaning a whole number. So 1 or 2 or 3 or 4. So how many rotations around the unit circle, essentially, is what K is standing for. The last piece of information we're going to have here is kind of hard to see because we only have one period of this function graphed. But if I were to put a pin in the origin right here, and again, I know that this continues on, and I rotated this graph around the pin in the origin, the left side and the right side of the graph would end up landing right on top of each other. So it has rotational symmetry about the origin. That means that the sine function is an odd function. Not even odd by numbers, but even odd by function type, meaning it has rotational symmetry about the origin. What that also means mathematically, and we'll start to see this more in the next chapter of this class, is that if I took sine and plugged in a negative number, I should get the opposite value of the positive number as my output. So sine of negative x would be the same as negative sine of x. Odd means opposite. Odd, opposite. Odd, opposite origin. Nice. Odd, opposite origin. Sound good? Do we see the sine curve? Starts at 0 and increases before coming back down and coming back up again. Let's move on to the cosine curve. The cosine curve, we're going to do the same thing. So we're going to be looking at our unit circle for now, all of the x coordinates of these values. What is the cosine of 0? 1. What is the cosine of pi over 3? 1/2. Then I'm jumping to pi over 2. 0. Cosine of 2 pi over 3. Negative 1/2. Cosine of pi. Negative 1. Cosine of 4 pi over 3. Cosine of 3 pi over 2. Cosine of 5 pi over 3. Gets me positive. And cosine of 2 pi again, 1. So again, we're getting these values from the unit circle as we went around for all of these radian measures. Those radian measures are on the x-axis because they're our input values. We can plot the output values of cosine. We'd be at 0, 1, pi over 3, 1/2, pi over 2, 0, 2 pi over 3, negative 1/2, pi, negative 1, 4 pi over 3, negative 1/2, 3 pi over 2, 0, 5 pi over 3, 1/2, and 2 pi, 1. So if I play connect the dots, the cosine function is also a wave, but it's a wave that starts, instead of at 0, it's a wave that starts at 1. If we kept drawing this, it would come back down and go back up and come back down and go back up over and over and over and over again. So much like the sine function, the cosine function itself has a domain of all real numbers. Because it would extend from negative infinity to infinity. What's the lowest this graph goes to? Negative 1. What's the highest this graph goes to? 1. So since its minimums and maximums are negative 1 and 1, and they don't extend anywhere else beyond that, the range is just from negative 1 to 1. Like the sine function, we can write down information about the zeros of this function. Where do you guys see, there's only 2 this time, the 2 zeros for this function? Pi over 2 and, but if I kept graphing this, those would repeat over and over again. So we have to write a general equation for the solutions or the zeros of this function, and it would be as follows. It would be the zeros will be equal to the first 0 that we saw, which was pi over 2, and every revolution of the unit circle after that. Continually rotate it by 2 pi, we get back to the same value of 0. The other 0 would occur at the second value of 0 that I see across the unit circle, 3 pi over 2, and every rotation afterwards, where k is an element of the integers, meaning it's some sort of number that we're multiplying 2 pi by to give me multiple rotations of the unit circle. If we extend the cosine function, and like I said, this is kind of hard to tell because I only gave you one period of the function, but if I were to extend this wave this direction and put a pin in the origin and spin it, it would not have rotational symmetry. However, because this would come back down, do you kind of see how it's repeating the exact pattern in the exact shape? Where I could fold this side on top of this side? That's called an even function. So an even function has symmetry over the y-axis, like folding symmetry, regular symmetry, over the y-axis. Mathematically, what this means for us is that whether you put in a negative input or a positive input, you get the same output out of it. So cosine of negative x will be equal to positive cosine of x. If odd, opposite origin, even is the same and is the y-axis. Not as cute like of a memorization thing there, unfortunately. So we have the sine and the cosine function, which are waves. Can look at the graph of the tangent function, which is significantly different in shape than the sine and the cosine function, but we're going to build it the same way. So I have some values for tangent from the unit circle I want us to fill out. What is the tangent of 0? Remember, tangent is sine over cosine, so you take the y value over the x value. It would be 0 over 1. What is 0 over 1? 0. So tangent of 0 is still 0, but keep that in mind for later because we're going to need that answer. Look at tangent of pi over 4. What is it? 1. How about tangent of pi over 2? That's our undefined because it would be 1 over 0, so that's undefined. How about 3 pi over 4? Negative 1. How about pi? 0. 5 pi over 4? Positive 1. 3 pi over 2? Undefined again. 7 pi over 4? And then 2 pi. Interesting. As a reminder from college algebra, when we did a bunch of functions that had undefined moments on them, what happens on a graph when our answer is undefined? Vertical asymptotes. So what we can do is we can go ahead and graph these vertical asymptotes at pi over 2 and at 3 pi over 2 so that we're prepared to have them be undefined values on my graph. But then we get ready to plot our points. We have 0, 0, pi over 4, 1, and then my vertical asymptote. 3 pi over 4, negative 1, pi, 0, 5 pi over 4, 1, and then a vertical asymptote. 7 pi over 4, negative 1, 2 pi, 0. Weird. How do we play connect the dots here? Remember that for when we did rational functions, you cannot touch or cross those vertical asymptotes, correct? So if I played connect the dots starting from 0, it would look something like this, and then I'd have to skim up towards the top. I jump all the way back down. It's called a jump discontinuity. so that I can continue to connect the dots in that middle little section between the two vertical asymptotes. Skim up towards the top, getting close to but never touching that vertical asymptote. Jump back down to finish the shape all the way up. Now obviously this would continue up and this one would continue down if we continued to draw these. These are no longer what waves. Sine and cosine are called sinusoidal waves. Tangent is not a wave, though it is a periodic function because it does repeat the shape over and over and over again. Let's talk about the domain, range, zeros, vertical asymptotes, and the type of function that tangent is. How would you describe the domain of this graph? You don't have to use fancy math words. Just give me some words to describe what x values we're allowed to use. Does it extend all the way from the left to the right? Yes, sort of, right? You're like, it does keep going to the left and it does keep going to the right, but we've got all these stopping points, correct? Here's how we're going to do this. We're going to say that the domain for this function is all real numbers except for all of the places where there is a vertical asymptote. Where is there a vertical asymptote? Pi over 2. When is the next vertical asymptote? It would almost be 2 pi k. But do you see how this repeats in a shorter amount than sine and cosine? How long does it take for it to repeat itself? Pi. So we're actually doing plus pi times k. Sine and cosine take 2 pi units to go all the way around the unit circle to repeat itself. But tangent, we repeat itself much quicker. We go through quadrant 1, quadrant 2, we're already ready to repeat tangent. So it has a shorter period. We'll get to that definition later. So its domain is kind of weird. It is all real numbers except for the places that there are vertical asymptotes. What's the minimum of this graph? Negative infinity. What's the maximum of this graph? Yeah, I mean, technically it doesn't have a minimum or maximum, but thank you for asking the question that I wanted. This gets the range to be from negative infinity to positive because it's an unbounded graph. There is no real minimum or maximum. Where are the zeros of this function? Where do you see it crossing the x-axis? 0, pi, and 2 pi. So this one, again, because tangent has a repeating time, a period, we'll get there later, that is much faster than sine and cosine, we're going to say the zeros appear at 0 and every repetition of pi after that. 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. Because it has a shorter amount of time it takes to repeat the tangent function, we get to just use pi instead of having to list out both. Now this also has a very interesting vocabulary word that we didn't have to put on the other ones. Sine and cosine don't have vertical asymptotes, but tangent does. So we can write a general equation for the vertical asymptotes, and you guys have already done that because we used it in the domain. We're saying that the vertical asymptotes of this graph will appear at x equal to 1 pi over 2 and every repetition of tangent after that. So 3 pi over 2, 5 pi over 2, 7 pi over 2. Again, this is hard to see on this graph because I didn't give you enough in the negatives. But if you were to put a pin in the origin and spin this graph on top of itself around, whoop, one side of the graph would land right on top of each other. So it has that rotational symmetry, which again means that this is an odd function, odd origin. And thus that tangent of negative x should be the same as the opposite of tangent of x. Odd opposite. Odd opposite. When we're wanting to adjust the height of the crest of the wave or the depth of the trough of the wave, we're going to be changing the a value in the transformation of sine, cosine, and eventually tangent. Tangent technically doesn't have an amplitude, but we're going to pretend like it does because it's actually helpful for graphing. This amplitude comes from the number that is being multiplied in front of the sine, the cosine, or the tangent. I only have sine written on this paper, but any of the three functions can be there. If it's multiplied on the outside of the function, that makes it a vertical dilation of the function. And so what we've done is we've taken the top and the bottom of the graph and we've stretched it, a vertical stretch or a vertical shrink. The way that we figure out what the height of the crest or depth of the wave should be comes from the formula that the absolute value of A should be equal to the maximum value minus the minimum value divided by 2. You'll notice that I am using the absolute value of A. So a follow-up question you may have is, well, what if A is negative? What does that mean? We'll write down that note for ourselves. We're going to take a note that if A is less than 0, meaning if the number you're multiplying on the outside is negative, then that just means that we have a reflection over the x-axis. A reflection over the x-axis. Amplitude itself is never negative, but if you have a negative A value, that means it has been stretched and flipped. Or shrunk and flipped. Another transformation we can apply to the function is by multiplying a number, but on the inside of the function itself. Multiplying on the inside. If it's multiplying on the inside, that means it's a horizontal dilation. And this has to do with the period of the function. So I'm not going to say that the period is b, so I put a little asterisk right there. It's related to b, but the period is not the exact number that you see there. The period of a function is the input value interval, usually time or angle, that it takes for a periodic function to complete one cycle or begin to repeat itself. The way that we find the value for b, or for the period, for sine and cosine is 2 pi divided by b. That is the period of the function, which is why I'm telling you it's related to b, but b is not the period. We use b to find the period. For tangent, though, you guys already noticed that it didn't take as long for the tangent function to start to repeat itself. So instead of the formula being 2 pi divided by b, the formula for tangent is just pi divided by b, because the typical period of a tangent function is much shorter. Here's where it'll be different from AP Pre-Cal in the letters that are being used. A phase shift is the letter D in this class. A phase shift is the horizontal shift compared to the graph of the parent function for the one that you're using. Much like in Algebra 2 or in college algebra, when we were adding or subtracting a number on the inside, we're just shifting the graph to the left or the right. So we're changing where the starting point of this sine or cosine or tangent function wave or graph would be. I'm going to have to zoom down, I'm so sorry. What we know from Algebra 2 or the college algebra version of this class is that if you see plus D, that means that your graph has shifted to the left. And if you see minus D, that means you know your graph has shifted to the right. That shouldn't necessarily be new, might be a little bit rusty from when we've done this before. But our phase shift is just taking the entire wave and moving it from side to side to give it a different starting point. So I like to think of phase shift as the starting value. Is it starting in the normal spot? The last letter we have left that we have not highlighted, which again is a different letter from AP Pre-Cal's CED, so it might confuse you a bit. We are adding or subtracting a number on the outside of this function. Sometimes it's in the back, so you would see it as sine of whatever plus 5 minus 5. But our book likes to put it in the front of the function. Either way, it's being added to the function itself. That is called the displacement or the midline of the graph, which changes the vertical shift, the vertical translation compared to the graph of the parent function. This one's normal, where plus a number goes up, minus number goes down. But we do have a formula for the midline or the displacement of this graph, and that formula is C equal to the maximum value plus the minimum value divided by 2. Amplitude we did minus, max minus min. Midline we do max plus min. It is the average of the maximum and minimum values. So what I'd like to do with this information and these 4 colors is go back to the functions that we already graphed on the other pages of these notes and add the information of the amplitude, period, phase shift, and midline for our parent functions. Again, clearly phase shift, it hasn't been phase shifted because it is the parent function, but I want to see that you understand the starting points. So I'll give you a second to catch up with the colors, and then we'll get started on our graphs themselves. So if we go back on our notes, just back it up a little bit to the sine function. I want to highlight and annotate with these 4 colors we've used for transformations what the amplitude, period, midline, and phase shift would be for the parent function. Stay with me on this. So amplitude is the height of the wave or the depth of the crest. So if I was annotating sine to see the amplitude, I'm going from the average, or where the middle line is, and up and down to the height of the wave and the depth of the crest. I think I said those backwards, but you get it. What is the amplitude of the regular sine function? How much did I go up or go down? 1, which means for every sine function, the amplitude is equal to 1 typically. If it's not equal to 1, if you see that your amplitude is higher or lower, that means your graph has been transformed in some way, and you would need to figure that out. The next question asked us to find the period of the function. How long did it take for us to do a full one of these graphs without repeating? 2 pi. So if we go from 0 all the way to 2 pi, we see that the period of the function is 2 pi. Therefore, in my equation, if the period itself is 2 pi, that means I did 2 pi divided by 1. So the b value for this graph, the b value would be 1, because 2 pi divided by 1 is 2 pi. So if your graph does not take as long to finish the full sine wave, your period has been changed and there is a b value other than 1. For phase shift, I like to see what starts the graph. So we're looking at the y-intercept. What is the y-intercept for the sine function? 0. So my phase shift, well, this graph technically doesn't have a phase shift. My phase shift would be 0 because this is the parent function. But we know then that for this phase shift, for the sine function is always going to start at 0 and then increase. If your function that you have in a question does not start at 0, but it's telling you it's a sine function, that means it has been shifted from side to side, and you would have to account for that phase shift, moving it to the left or to the right. The last thing we have here is the displacement or the midline. What is the midline of that graph? 0, yes. Because this line right here that we had already kind of drawn on is in the middle of the max and the min. We can highlight it. I like to do a dashed line for this since it is my middle of the graph. All the way across this graph, and we would know that our midline is the x-intercept. Is the x-axis. If your graph has a midline other than y equal to 0, it has been shifted up or shifted down, and we'd have to account for that in our formula. So for the parent function, this is the information we know. The amplitude is 1, the period is 2 pi, there is no phase shift, and the midline is 0. You will be working with transformed graphs that will be different than that, so you need to be paying attention to comparing it to the parent function. We're going to go ahead and do the same thing for the cosine function. And I realize that you're going to start seeing a lot of the same answers. We're doing this amplitude, period, phase shift, and midline to the parent functions, which are like the boring ones, if you will, the basic ones. But let's go through it again. If I were annotating on this graph to find the amplitude, that means I'm going from the middle of the graph up or down to meet the maximum and minimum values. What is the amplitude of the basic cosine function? It is still 1. So the amplitude of the basic cosine function is still 1. Then we get to the period. How long did it take for us to finish getting all of the values of cosine? From 0 all the way to 2 pi. So the period of the regular cosine function, the amount of time or angles that it takes to finish, is 2 pi. And what that means to me is that the b value is 1 because 2 pi divided by 1 is 2 pi. So it allows my period to be the entire distance of the basic function. Here's one, this one gets different than sine. What is the starting place? What is the y-intercept of the cosine function? 1. Ooh, interesting. Instead of starting at 0, the cosine function starts at 1. However, because this is the basic one, we would still say that the phase shift is 0. This is the basic function. All of them should start at 1 and decrease. If your graph does not start at 1 and immediately decrease, and you are told that it's a cosine function, you probably have shifted it from side to side and need to account for that in the phase shift. And then last but not least, we need our midline. What's the midline of this graph? Also 0. Again, basic parent function. But if your graph does not have a midline of 0, that means that you have shifted it from normal, and we need to account for that in the formula. The blue represents the period, yes. And I know it's going like the same distance as the purple. Is that what's confusing you? So the blue is starting at 0, stopping at 2 pi to show that that's one full wave. The purple line is showing me where the middle of the graph is. So like in between -1 and 1 is the number 0. Does that make more sense? Okay. And tangent has some different answers that will make it make more sense too. If we go over to tangent, same vibe. We're going to do all of the same information, except that now amplitude is technically the maximum value to the midline or the minimum value to the midline. But this graph does not technically have maximums or minimums. We discovered that earlier. However, the number in front of the tangent function kind of works as a fake amplitude. So I'm going to put it in quotations. This fake amplitude tells me from the midline of the graph up to the other important inflection point. So I still have an amplitude for the tangent function. It's not a real amplitude because it's not going to a maximum or a minimum, but it is an amplitude because it helps me graph the function. What is the fake, quote, amplitude of the tangent function? It's still just 1, because the height of this little stick that I've drawn on here from the middle of the graph to the inflection point is 1. This is 1. This is 1. This is 1. It's not a real amplitude, but it works like an amplitude. And next up, I have the period. How long did it take me on this one to draw a full cycle of the tangent function? Just to pi. If we start at 0 and increase, the next time we're going to 0 and increases is right here at pi. This is why for all of the domains and the vertical asymptotes and the zeros, we didn't put plus 2 pi k, we just put pi k. But either way, that is the normal period of the tangent function, which still means that b is going to be equal to 1 because the formula changes for tangent as opposed to sine and cosine. So pi divided by 1 is still pi. Following along like we did before, the phase shift will tell us where to start graphing. And this graph should start at 0, 0. That is the typical or normal y-intercept for a tangent function. So if your graph does not start at 0, 0 and you're told it's tangent, we may have to shift it from side to side. So our phase shift, again, this is the normal one. So this one has a phase shift of 0. But it lets us know that tangent starts at 0 and increases. Starts at 0 and increases. The last thing we want to write about is the middle of the graph, the midline. Where is the middle vertically of this graph? It's still at 0. Again, basic parent functions all have a lot of the same answers. But if we have this function that has a midline at 0, we have not scooted this graph up or down at all, and so the midline is the same. The midline of the basic tangent function is y equal to 0. If your graph has been moved beyond that, it has been moved up or has been moved down to where the middle points are not on the x-axis, your midline would be different. The main gist of today is to start to get the shapes of the sine, cosine, and tangent functions so that we can start to write equations for some that are a little bit different looking than these basic ones. And it comes down to being able to write the A, the B, the C, and the D letters that give you the different parts visually of the graph. Now I know there are literally like not example problems in our notes today, but we're already tired of listening to me, I can tell, which means that your practice problems are coming from the homework immediately. And I want you to log into your homework and get started on it because I want you to see the kinds of questions that I would ask you for these graphs before you leave and then have to ask somebody else for help. I want to be the one to help you. I'm selfish today. Ask me questions. Layla's looking at me like I'm crazy. Yes.